Hello, welcome to your Unit 5 review. So these first three is the second part of the fundamental theorem of calculus. We're doing a derivative of an integral. Now this one, both of the boundaries are constants, and a derivative of a constant is just going to be 0. So we just end up with nothing for that one. For this one, we're just going to take x and plug it in for t. The derivative and integral undo each other, so you just end up with what's there. So tangent cubed of 4x. All right, this one, the boundaries are reversed. The variable is in the lower boundary. So we're going to need to put a negative since they have been reversed. And also we're going to need to do a chain rule and chain on the derivative of the 2x cubed. So you can put that at the end. I'm just going to put it out front. It doesn't make a difference. That would be 6x squared. And then you're just going to take that 2x cubed and put it in for t. All right, so you're essentially just plugging that in. This one just had a chain rule and the boundaries were reversed, but that is all that there is to that. All right, for number 4, we are given this f of x equals, this is an accumulation function. It's a function in terms of an integral. We're given this initial condition, f of 7 equals 4, find f of 9. So it's going to be 4 plus, and then we want to accumulate from 7 to 9. So it doesn't always start at 0. This one's starting us at 7. So from 7 to 9, sine of 3t squared dt. And we are going to put that in the calculator. So make sure that you are in radian mode. If you're doing sine, cosine, tangent, if you're doing anything with trig, you need to check that you are in radian mode. And then we're just going to type that in. And you're using math 9 for the integral. And make sure you do 3 decimal points and you can truncate. So just take the first 3 that you see. So there we go, 3.989. You can round it up if you want, but I think it's easier to just take the first 3. All right, so for this one, we have an accumulation function. It is starting at 0, and we're asked to find all of these values. So what I would do first is go and find all the areas under the curve. So first, let's do this little triangle here. So it would be 1/2 base times height. I'm just going to write these off to the side. So 1/2, the base looks like 1.5. That would be 3/2. Height is 1. So that would be 3/4, but it is below sea level, so -3/4 for that part. This triangle here is the same as that triangle, so this would be a +3/4. And then it would be nice if you could do this whole triangle, but we have to split it right here, and that's because our accumulation starts at 0, and so we have to split that at 0. So let's do this little guy. That's a trapezoid. 1/2 times the height, which this is the height because it's on its side, and then add the bases together. So this base is 1, this base is 1/2. So that would be 3/2 times 1/2 would be 3/4. That is also 3/4. And then this little triangle is 1/2 base times height. And so that little guy is 1/4. All right, so I'm going to break this up to do this triangle. 1/2 base times height. That would be 2 times 1. So that would just be 1, but again, it's underneath the x-axis. So it's like a D accumulation. And then this is just a rectangle, base times height. It would be 3, but we're going to call it -3, again, since it's underneath the x-axis. So I would just go and find all of those first. And then when we come over here to answer the questions, we already have them all. So plugging -4 into this, that means we want to accumulate from 0 to -4. So that is from here to here. So we're going backwards. So all of these are going to be opposite. So it would be a -3/4, a -3/4, a -3/4, and a +3/4. Either way, these two are going to cancel, and so that will just be -3/4. All right, plugging in -2.5. Now we want to go from 0 to -2.5. So that's from here to here. And so we're still going backwards, so it's still like opposite day. So we're going to have -3/4 and -3/4. That would be -3/2. It would be -6/4, then reduce that, -3. All right, plugging in 1. Finally, we're going forwards. We want to accumulate from 0 to 1, so that's just this little triangle, so 1/4. Plugging in 3, so from 0 to 3, so that's from here to here. So we have 1/4 minus 1, that would be -3/4. And then plugging in 6, so from 0 to 6, that's from here all the way to the end. So that would be 1/4 minus 4. So let's see, 1/4 minus 4 would be 16/4. So -15/4. Now these ones are derivatives. Derivative and integral cancel each other out. So it's just that point on the graph. We're no longer accumulating area. We just want that point. G prime of 1 is just this point here. That would be 0. And then G prime of 3 is just this point here. That would be -1. So again, G is an accumulation function in terms of an integral. If you do G prime, if you do that derivative, you're just going to get what's inside, which is f of x, which is this function. It says f of x is the function shown. So those are just that point on the graph. All right, state intervals where G is increasing and decreasing. This is the stick-it note that we made. All right, G is increasing, and I just say f prime, f double prime, it just pretend it says G. All right, G is increasing where the derivative is positive. Remember, we're looking at the derivative graph. This is G prime, or f of x. So increasing would be where this graph is positive. That means above sea level. Decreasing would be where it's negative. That means below sea level. So increasing would be from -2.5 to 1. And decreasing would be everywhere we're below the x-axis. So that would be -4 to -2.5. And then also from 1 to 6. And then concavity, so your original graph is concave up where the derivative is increasing, concave down where the derivative is decreasing. And again, remember, we're looking at the derivative graph. This is G prime. All right, so concave up is going to be where this graph is increasing. So that would be -4 to -1. And concave down would be where this graph is decreasing. So that's from -1 to 3. And then we have no concavity from 3 to 6. The graph would be linear for that portion. And then state locations of relative extremes. So we have a relative minimum at -2.5. It's where the derivative changes from negative to positive. So below to above. Negative to positive would be relative minimum. So relative minimum at x equals -2.5. And then we would have a relative maximum at 1. Derivative changes from positive to negative. So positive to negative means that is where we have a relative maximum. All right, you are shoveling snow off your driveway while it is snowing. So this is a rate in, rate out problem. Snow is landing on the driveway at a rate in cubic feet per hour. So it's a volume per hour. This is your rate in. And then you're shoveling the driveway at a constant rate of 3. So that's your rate out. We're starting with nothing. So initial condition is that there's nothing. So what is the net rate at which snow is landing on the driveway at time 4? Net rate means you have to look at the rate in and the rate out. These are rates. We just need to plug in 4 and subtract them. So it would be S of 4 minus H of 4, which H of anything would just be 3. All right, so we're going to plug in 4 to this. So 30 e to the -1/2 times 4 plus 1, and then minus 3. So it's rate in minus rate out. And I'm just going to type that in, and we will get our answer. -1/2 times 4, that would just be -2, and then plus 1 minus 3. So 2.060. And it is a rate, and so it was cubic feet per hour. So remember, a rate is something per something else. Now B is how much snow is on the driveway at time 4 hours. So that's an accumulation. We want to accumulate snow. Now the driveway was initially clean, so we start with nothing, but I'm still going to put 0 plus just to remind us that if there was snow to begin with, that number would go here. So nothing plus, and we want to accumulate from 0 to 4, and then it is rate in minus rate out dt. And we're going to put that in the calculator and get our answer. So math 9, 0 to 4, rate in 30 e to the power negative 1/2 x plus 1, and then minus 3 for the rate out dx, and that will give us our answer. So 43.879. I'm just take the first 3 decimal points. Now that's not a rate. We accumulated snow. So it's just the amount of snow. So cubic feet of snow. It's not a rate anymore. It's just an amount. C is set up the integral equation that would give the time x at which all of the snow is shoveled off the driveway. So that means it is all gone. So it's kind of what we did right here. It's just instead of a 4, we want to have an x there. So it's going to be integral 0 to x. Nothing is what we started with. And then in here, you're going to have rate in minus rate out dt, and we're going to set that equal to 0 because we want all the snow to be gone. And letter D, is it possible to solve that, yes or no? So what you want to do is compare the two rates. And so I'm going to go to y equals, I'm going to put the rate in into y1. Sorry, I can't type and talk at the same time. So that goes into y1, and then the rate out goes into y2. And we're just going to take a look at the graph. So I always hit zoom 6 to start with if I don't have a window given to me, because it'll just put it negative 10 to 10. We can always adjust that. But the answer is yes, we will be able to solve this. You can see where they intersect, and the rate of your shoveling is greater than the rate at which it's snowing. So you will eventually catch up. So the answer is yes. Yay, we're going to be able to shovel all the snow. Now, justify. So you have to compare these rates in some capacity. So I would say h of t, and you can kind of word this however you like, but you want to use a word like greater than or less than, like you have to do a comparison. H of t will be greater than S of t at some point. And if you even wanted to be like really thorough, you could find that point. Like if you wanted to calculate that, you can go to second trace where it says calculate there. So calculate intersection. And it's going to ask you first curve, second curve, guess. You can pretty much just hit enter for all those. First curve, enter, second curve, enter, guess, enter. And it'll tell you when your shoveling is going to catch up to the snowing. So if you wanted to even be more specific, you could say instead of at some point, you could say at 5.416 hours. But what I would be looking for is this, the greater than, like the comparison of the two rates is what's important there. You want to compare them. All right, number 11, the rate of change. We're given a derivative. This is a rate in miles per hour, something per something else, of the distance of a car driving closer and further away from home is given by this. We have an interval from 0 to 11 hours. Assume the car is initially at a distance of 65 miles from home. So that's your initial condition. The car doesn't start at home. So let's take a look at this rate graph. So I'm going to go back to y equals, clear both of these out, and I'm going to type that. Okay, and I'm going to go to window. We were given a window of 0 to 11 hours. And we can always change this. Let me see what it looks like first. So we want to do 0 to 11. That does go off the graph, but we can see everything that we need to see. So here the rate is negative. That means the car's driving closer to home. Remember, it doesn't start out at home. It starts out 65 miles away. So it drives closer. And then for all of this positive part, it drives further away. And then for this portion, it drives closer to home. So that is what is going on. So letter A, when is the car closest to home during the first 11 hours? Well, it starts out 65 miles away. And for this portion, it drives closer to home. So at this point right here is when it's closest before it starts driving further away again. The other way you can think about that is the rate changes from negative to positive. So negative to positive means minimum. So we need to calculate that. So I'm going to go to second trace. I want a 0 where it touches the x-axis. Now it looks like it's really, really close to 2. So I'm going to make my left bound be 1 and my right bound be 3, and then I'll guess 2. I can tell it's like a little bit less than 2, but close enough. So left bound, I'm going to do 1, enter. Right bound, I'm going to do 3, enter. Guess, I'm going to do 2, enter, and it will tell me that. So yeah, a little bit less than. So 1.700, you know what, I'll go ahead and round this up so it's not a 0. 1.701 hours is when the car is closest to home during that time interval. What did I just say? It was 701. It says, what is its distance at that time? So what we would need to do is store this value. As of right now, the calculator has it as x. So what I'm going to do is quit out here, go back to the home screen, hit X, enter, that'll bring it back, and then I'm going to store it as A. So here's your store button. You're going to hit store, that'll put a little arrow on there, and I'm going to do alpha A, enter. So store alpha A, enter. You can store it as whatever letter of the alphabet you want, but A is just convenient because it's right next to alpha and it's the first letter of the alphabet, right? So we're going to store that as A. And then to find where the car is at that time, you're going to take where it started plus its accumulation from 0 to A of R of T dt. So it's where it started, initial condition plus accumulation. So I'm going to type 65 plus integral from 0 to A, and then I have to put this function in there. All right, and that will tell us where the car is at that time. So 58.372 miles. And I want to make sure that makes sense. So it started at 65 miles away and it drove closer to home. So you should get an answer smaller than 65. Letter B, we're going to basically repeat that process except when it's furthest away. So I'm going back to the graph. This is when the car is furthest away. All of this positive part is when the car is driving further away from home. And then here's where it starts driving back towards home. So this would be the maximum. Also, you can think of it as a change in the derivative from positive to negative. So positive to negative means maximum. So this window was 0 to 11. So this would be really, really close to 10. So when I calculate this, calculate 0, I'm going to do 9 as my left bound, 11 as my right bound, and then 10 as my guess. So we get 9.747 hours. And we're going to do the exact same thing we did in the previous problem, store that as A. So as of right now, the calculator has it as X. I'm going to quit out of here, go back to the home screen. Let me clear all that out. I'll hit X, enter to bring it back, and then store alpha A, enter. So store it as A. Now, the kind of nice thing is we want to do this all over again. So here, I'll write it again. It's just A is now stored as this other value. So we're going to get a way bigger number because the car is way further away from home. You don't have to type it all over again. You can just go back up until you find that. There it is. And when you hit enter, it will type in the new stored A value for you. And so, yeah, we got a much bigger number because the car is way further away. So 214.077 miles away from home. So we found the minimum and the maximum on that time. Letter C, find the value of integral from 0 to 11 R of T dt and explain what it means. The most common mistake I get on this one is people put the 65 plus out front. I'm not asking for that. It's just literally this. So you can go back and bring this back if you don't want to type it all over again. You just have to change the A to an 11 because we want that upper boundary to be an 11. And then you have to delete this 65 from out front. This is your delete key right here, DEL. So I'm just going to delete that. You can type the whole thing all over again if you want. I'm just trying to save you some time. All right, so 128.104. And then we're going to explain what that means in the context of the problem. Now, because there's no absolute value here, this would be displacement. So 128.104 is displacement in miles. And then you have to say from when to when. So from 0 to 11 hours. So it is the displacement in miles from 0 to 11 hours. Letter D is the exact same thing except with an absolute value. Now, the bad news here is you can't like just insert an absolute value in there. So we are going to have to type the thing all over again. Your absolute values in the math menu, go over to numbers, and it's the first one. It says abs. So in your math menu there. I'm just looking that over, make sure I typed it right. DX. Now this one sometimes takes a minute with the absolute value, so you just got to be patient. Just don't hit any other buttons. It will eventually come up. All right, there we go. And it's a way bigger number because when you have the absolute value, it treats all of the movement as positive. And so it's going to be this exact same sentence, but instead of displacement, it is total distance. So 183.307 is total distance in miles from 0 to 11 hours. So this is the same kind of question. Just like A and B were the same kind of question, except this was the minimum and this was the maximum. These are the same kind of question, except this one's displacement and this one's total distance. All right, and then letter E, we want integral from 0 to 11 R prime. So an integral and a derivative are inverses. They're going to undo each other. You're just going to be back to regular old R of t such that 0 to 11. So again, these cancel out. It's just regular old R of t 0 to 11. So upper boundary minus lower boundary. And so we're going to plug 11 into the function, plug 0 into the function, and subtract them. So negative 1/4, and we're plugging in 11. So 11 cubed plus 5/2, and then 11 squared, which would be 121. I'll just go ahead and type that, and then minus 6. All right, so negative 145/4. Let me see what that would be as a fraction, or I'm sorry, as a decimal. Here we go. Negative 36.25. Let me go with that. Minus, and then if you plug in 0, you're just going to get negative 6. And so that would cancel the negatives plus 6. You would have negative 30.25. And then we have to explain what that means in the context of the problem. So what we plugged into was R of t. We did the rate at time 11 minus the rate at time 0. So it's how the rate changed. And since it's negative, the rate decreased. So we're going to say the rate decreased 30.25 miles per hour. It's a rate, so something per something else. And then again, you want to say from, and then the boundaries. So from 0 to 11 hours. If this was positive, we would say the rate increased that much. Again, we did R of 11 minus R of 0. So it's how the rate changed from 0 to 11 hours. All right, so again, we've got an accumulation function. This one begins at 6. So just be aware of that. That's where we're starting. And I'm going to first find all of these areas. I think that's easiest if you just go and find all the areas first. So triangle 1/2 base times height. The base is 3, the height is 4. So that would be 6. It is below sea level, so negative 6. And then this is the same triangle up here, so positive 6. And then the semicircle is 1/2 pi r squared, and the radius is 3, so that is 9/2 pi. Positive because it's above the x-axis. And so again, if you do this derivative and integral cancel out, you just get f of x, which is this graph. So you're looking at g prime. So like if you think about your stick-it note, this is the graph that you're looking at. You're looking at the derivative graph, but you're answering questions about the original function. And again, usually this is the one that they give you typically, like most of the time. So state the critical points. That would be where the derivative equals 0. This is your derivative graph. So it equals 0 at 0 and 6. They didn't say to justify, but if they did, it would be because g prime equals 0 there. So we're going to look at both of those critical points. And it says interior critical point. If you happen to have a critical point that's also an end point, then you wouldn't need to write a sentence about those. An end point cannot be a relative maximum or minimum because it's not relative to anything else. All right, so we're going to write a sentence for 0, a sentence for 6, location of relative maximum, minimum, or neither, and then justify. So we'll have to put because. So at 0, the derivative changes from negative to positive. That means minimum. And you want to start your sentence g of x is or g of x has, because that's the function that you're talking about. So g of x has a relative minimum at x equals 0 because g prime changes. Oh, let me erase that. From negative to positive, there, barely fit that. All right, and then at 6, we don't have a change. The derivative does not have a change. You can say it stays positive. I usually just say does not change sign there, however you want to word that. So g of x has neither a relative maximum or minimum at x equals 6 because g prime does not change sign there. All right, state the intervals where g is increasing and decreasing. Increasing is where your derivative is positive, that means above sea level. Decreasing, negative, that's below sea level. So g of x is increasing from 0 to 9. G of x is decreasing -3 to 0. It didn't say to justify, so I'm not going to do that, but it would be because g prime is positive there and because g prime is negative there. G prime is your source that you're citing for all of your justification. All right, absolute extrema, that is the candidate test. Your candidates, you're going to plug into the original function, which is this accumulation function here. Your candidates are the end points, so -3 and 9, and your critical points 0 and 6. So be careful, this one's accumulation starts at 6. So if we plug in -3, we want to accumulate from 6 to -3. We're going backwards, so everything counts opposite. It would be -9/2 pi plus 6. All right, for 0, again, going backwards, it would just be -9/2 pi. If you plug in 6, you're just going to get 0. If you accumulate from 6 to 6, you didn't go anywhere. And then from 6 to 9 would be this area, so that is 6. So g of x has an absolute maximum of, what is the biggest one there? 6 at x equals 9. And then g of x has an absolute minimum of, and I guess this would be the lowest one, -9/2 pi at x equals 0. And it says justify, but your justification is the chart. You've shown every single candidate, so you're good there. All right, points of inflection. That means a change in concavity. So that's where your derivative changes from increasing to decreasing or vice versa. All right, so we are increasing all the way until here. So that's 3. So x equals 3. And then we decrease and then we change direction. I should say change direction. Change from decreasing to increasing at 6. So 6 is both a critical point and an inflection point. And it's where the accumulation starts. So that's like a really important point on this graph. So x equals 3, x equals 6. concave up and concave down. G of x is concave up where the derivative is increasing, concave down where the derivative is decreasing. So we are concave up from -3 to 3, and then also from 6 to 1. And it didn't say to justify, but it would be because G prime is increasing there. And then concave down would be from 3 to 6, and it would be because G prime is decreasing there. So again, G prime is the graph that you have. So that's your source that you're citing. And then sketch a graph. So let's start with all of the points that we have so far. So -3, 9/2 pi plus 6. Let me just type that in the calculator for the ease of doing that here. -9/2 pi plus 6. So around -8, -8 and a little bit. All right, and then 0, -9/2 pi. So that would be the same thing, except just without the plus 6. So that would be like around -14, like -14 and a little bit. And then 6, 0, and then 9, 6. So those are the end points and the critical points. That's what we had on our chart here. You also need the inflection points. Now we did 6 already because it was both a critical point and an inflection point, but we need to go back and get 3. So if we plug 3 in, we want to accumulate from 6 to 3. That's still going backwards. That would be negative, and it would be half of this. So 9/4 pi. So let me see, -9/4 pi. I'm just going to type that in real quick. Around -7. So that would be 3, and then around -7. And then you just want to connect it with the correct concavity. So we want to be concave up from -3 to 3. And then concave down from 3 to 6. So try and bend it the other way. And then concave up again from 6 to 9. So that's what our graph would look like. All right, so this is your integration by parts. We're going to have to decide what we want to let U equal and what we want to let dV equal. If you mix it up, it just won't work. And then you'll be like, oh, let me switch it around. So here we're going to let U equal X, and then dV is going to be sine of 9x minus 1 dx. So then we're going to find du and v. So we're going to take the derivative of this, derivative of x would just be 1 dx. And then here we're doing the antiderivative. So it's difficult, you have to balance it in your head because one is one way and one is the other. This we're doing a derivative, here we're doing an antiderivative. So you have to come up with a function that if you did the derivative, you would get sine. That would be negative cosine. And we would need a 1/9 in there to adjust for the 9. So negative 1/9 cosine 9x minus 1. And if you want to check, you do the derivative of v, you're going to get dv, right? And it's kind of like there was also a u substitution in there. We had to do a 1/9 to adjust for the 9. All right, so this is going to be u times v. So we're going to multiply these together. That would be negative 1/9 x cosine 9x minus 1. And then it's minus integral v du. Now, when we put this in here, this negative and this negative will cancel. So I'm going to go ahead and change that to a positive. It'll be 1/9 cosine 9x minus 1 and then dx. All right, so it was u times v and then minus integral v du, but the negatives canceled out. So this first part I'm just going to bring down to the next line. And then we're going to do this antiderivative. So you need to come up with a function that if you did the derivative, you would get cosine, and that would be sine. Derivative of sine gives you cosine. And again, there's a u substitution in there. It's just a simple one. You have to adjust for the 9 with a 1/9. So we already have a 1/9 there. 1/9 times 1/9 would be 1/81st. And then plus c at the end. All right, this is going to be your partial fractions. As this is written, there's no u substitution that's going to work for this. So off to the side here, we're going to have 20 over, and then I'm going to factor this. It'll split into x plus 1, x plus 6. And we want to split that into 2 separate fractions. And we have to figure out what the numerators are going to be. So a over x plus 1 plus b over x plus 6. And then what you do is go through and multiply by x plus 1, x plus 6 to all 3 of these. So if you multiply x plus 1, x plus 6 here, you're just going to get 20, which is the idea. You want that to cancel out. If you multiply x plus 1, x plus 6 here, the x plus 1s are going to cancel. You'll have a times x plus 6. And then this one, the x plus 6 is canceled. You'll have b times x plus 1. So we're going to let x equal what would make those 0 one at a time here. So if we let x equal -6, then what we're going to get is 20 equals, this would be nothing. And if x is -6, this would be -5b. And so we get b equals -4. And then we're going to let x equal -1. That will give us 20 equals 5a. This part would go to 0. That's why we chose that. That was the whole idea. And so we get a equals +4. So we're going to put the a is +4 and b is -4 back in here and put it back into the integral. And the whole purpose of that is it breaks it into like 2 separate problems, because you can't do it as it is here. You have to break it into 2 separate problems. So this would be 4 over x plus 1. And then this one is -4, so it'll be -4 over x plus 6. And now each of those is going to be ln. So this would be 4, when we do the antiderivative, they'll be ln. So 4 ln of x plus 1 minus 4 ln of x plus 6 plus c. So again, the whole idea with the partial fractions is you're breaking it into 2 separate problems so that you can do the antiderivative. All right, so here we have the improper integrals. So you can't have an infinity as one of the boundaries. So we're going to rewrite it as limit as b goes to infinity. And you can use whatever letter of the alphabet you want. Typically see a if it's the lower boundary and b if it's the upper boundary, because you don't think of it as integral a to b. So I'm going to use b. It really doesn't matter. I guess you can use anything you want except x. All right, and then this would be integral from 1 to b. And so essentially you've just moved the problem somewhere else, moved it outside of the integral. And then I'm going to rewrite this as 5x to the -7 dx. And so we're going to do the antiderivative, and then we'll do upper boundary minus lower boundary. And then lastly, we'll evaluate the limit. So you would have to add 1 to this power. That would make it -6. And so you would need a -1/6 out front. But there's already a 5 there. It'll be -5/6 from 1 to b. And yeah, you have to write that limit every single time. And so we're going to do upper boundary minus lower boundary. So if you want to set it up blank, we're going to do upper boundary minus lower boundary. So if you plug in b for this, I'm going to bring it back down to the denominator. You would have -5 over 6b to the 6. All right, so you have that -5/6, then this negative exponent comes back down. And then if you plug in 1 to any power is just 1, so you're going to have -5/6. And so lastly, we evaluate the limit. As b goes to infinity, this denominator gets astronomically large, which means that this part goes to 0. If you have an astronomically large, an infinitely large denominator, it's going to go to 0. So this part goes to 0, and then minus negative is going to cancel 5/6, and so you just get 5/6. The other way you can look at this, and this is just foreshadowing because we're going to do these infinite series later, it is what's called a p series. So you can notice, oh, p is 7, and so since that's bigger than 1, let me write out the whole thing here. That's going to equal, well, we have this 5 here. So 5 times 1 over p minus 1. So 1 over p minus 1. So that would be 1/6 times 5 is 5/6. So if you notice that it's a p series, that is a little bit less work because you kind of have like a little formula for that. All right, and then this last one, you have to notice that you have a vertical asymptote at -1. Or you're going to have a 0 denominator at -1, I should say, because actually that's not going to be an asymptote. When you factor this, that's going to cancel out. Anyway, you have a discontinuity at -1 because you get a 0 denominator there. So we're going to have to break this into 2 separate integrals. So we're going to integrate from -2 to -1. And this is going to be like a lot of writing, but you essentially just write the same thing over and over again. It's more like notation than anything else. And then we're going to go from -1 to 5. So from -2 to -1, and then from -1 to 5. And yeah, I'm sorry, I misspoke there. It's not going to be a vertical asymptote. It's going to be a whole because it's going to cancel out here once we factor this. All right, so you can't have that as one of the boundaries because it causes you a 0 denominator. So we're going to do the same thing that we did here. I'm going to call this one B because it's the upper boundary, and I'll call this one A because it's the lower boundary. Again, it doesn't really matter so much. For this one, we're approaching from the left. If you think about your number line from -2 to -1, you're going to approach -1 from the negative side. And then I'm going to go ahead and factor this. So that's going to split x plus 1, x minus 4. And so see, the x plus 1s are going to cancel there in a second. Oh, I forgot the integral. Integral from -2 to b. I'm sorry. We brought the limit out front. We want to approach -1 from the left side. Integral from -2 to b. So you put that limit out front and just change the boundary to b. And then this one's going to be the same thing. I'm going to, again, use A because it's the lower boundary, and we're going to approach -1 from the right. If you think about your number line, -1 to 5, you would be approaching -1 from the positive side. And so that would be from A to 5. And again, I'm going to factor this, it's going to count to the exact same thing we did over there. So these are going to cancel. And then we're going to do the antiderivative. So again, it's just a bunch of writing all this notation over and over again. So those are gone. We're going to do the antiderivative. So for x, that would be 1/2 x squared, and then minus 4x, such that -2 to b plus, then again, I'm going to write all this notation again. This is going to come out to the exact same thing as it did right here. It's the same problem, such that from A to 5. So now we're going to do upper boundary minus lower boundary. And then lastly, we can evaluate the limits. All right, so I'm just going to set this up blank. We're going to do upper boundary minus lower boundary. Now, if you plug in b, you're just going to get 1/2 b squared minus 4b. And if you plug in -2, let's see, that'll be 4. Half of that is 2. And then plus 8, so that'll be 10. All right, and then same exact thing over here. Again, this is a lot of like rewriting the same thing over and over again. We're going to do upper boundary minus lower boundary. So if you plug in 5, that'll be 25 halves minus 20. And then if you plug in A, basically just recopying that with an A in it. All right, so now we can evaluate the limits. So we're going to plug in -1 for B. So that would be 1/2. And then plus 4, and then we have minus 10, plus, and then over here we've got the 25 halves minus 20, minus, let me leave these parentheses here, and if we plug in -1, we will get 1/2 plus 4. I would be done with this problem at that point. If you want to simplify that down further, you can, but I recommend against it because if you mess it up, then it's going to be wrong. So just stop there. And again, my pep talk about that is it's a lot of writing, but it's really mostly notation. The actual math, like the antiderivative that we did, was not really that bad. And then you just end up plugging in -1 at the end. So you just end up writing the same thing over and over again a lot of times. I believe in you. You can do it.